All right, so we're going to go ahead and cover conservation laws when it comes to circuits. So the inherent idea of conservation laws is the fact that you really can't just make more or less of anything. So when it comes to currents or voltages, it's kind of like the same thing with when it comes to water. Like in your hydraulic system, you have a finite amount of water, so you can't make more water unless you actually input more water into the system. So with that in mind, there's two conservation laws. So one of them is the Kirchhoff current law, and the other one is the Kirchhoff voltage law. I'm going to first cover the Kirchhoff current law because this is the one that's a little more commonly used and kind of very easy to explain. So again, this is the Kirchhoff's current law. All right, so the inherent idea of this is when it comes to the hydraulic the analogy is that you have this sort of pipe that goes in like this. It connects like this. It's kind of like this T tube. You're going to have like multiple things that go in and out at once. And the inherent idea is that when I have like water flowing in this one direction, the amount of water that flows in here must equal to the sum of the water that flows out here. So if I just call this, flow 1, this is flow 2, and this is flow 3, you can effectively have a formula that says flow 1 is equal to the sum of flow 2 plus flow 3. And you can't have it so that it's anything more or greater than this. And so with that in mind, there's also another thing to keep in account where, say you have it going in the other direction. So it goes in like this. This can't logistically work, because what's going to happen is if all the currents go into this one general direction, the amount of water in here is going to build up, and it's just going to become like a near infinite amount supply of water for some strange reason. And there's going to be like no water flowing throughout the rest of your hydraulic system. So the idea behind this is that inherently at this one node point, which is right here, so this is a node. So it's exactly the same thing as we discussed earlier with the idea of like these wire connections, the exact same node, they have the same voltages. The idea is that at these nodes, the total sum of current that goes in here is equal to 0 because everything that goes in must come out. That's the inherent idea of the Kirchhoff current law. So with that, I can go ahead and just draw some sort of generic circuit here. I'm going to use a different color. We're going to use red to discuss this. So again, these are parts right here. I'm just going to just be a little bit creative here and just go ahead and draw something like that. And then we have some sort of connections right here. And again, these are nodes. So this is like one of the bottom nodes. This is one of the top nodes. And again, the idea is that all the current that goes in here or goes in here must equal that current that goes out, like that. So with that in mind, if I say like this is current 1, this is a current 2, and this is current 3, I know that current 1 is equal to current 2 plus current 3 is inherently the idea of this Kirchhoff current law. Another thing to keep in mind is that when it comes to the general standard of explaining how currents work, it's not the actual flow of electrons. It's actually the flow of the positive charge carriers. So it's actually the reverse flow of the electrons. The particular reason why we decided to do that was that when Benjamin Franklin was figuring out like these charged particles, he ultimately picked that it was the positive charged particle that was moving, even though in reality it's the electron. But with that in mind, we decided just to keep it with the context of it's the positive charge movement. So the inherent idea you can think about that is like when electrons are moving away towards something, that general region is becoming more and more positive. So the idea is that when electrons flow in one direction, the positive charges move in the opposite direction. It's kind of like the exact same idea as when it comes to like fluid flow, where if a fluid moves in one direction, the idea is like there's going to be less fluid in that direction, in that area where the water was moved out. It's kind of like that idea. So again, the idea is that with currents, it's not the electron movement, it's the movement of the positive charges. Just a small thing to keep in mind when you see circuits and you actually analyze them. Another thing to keep in mind too is that in fact, like you can in fact have like negative currents. So the idea of a negative current in this case, so let me just go ahead and just draw an example. So say this is my little thing that this is flowing through. So this is just some sort of component, and the current is going in this one direction. If I say that this is going in like -5 amps, that pretty much means that it's going 5 amps in the other direction. So really the negative sign just indicates the directionality of it, generally speaking. So these are just the exact same too. So technically what I could also say is that I can say that this current over here goes in the opposite direction but that's the negative current. So I can actually, in fact, say over here, let me just grab some space. So I can also arbitrarily select points when it comes to the directionality of these currents. So I can, in fact, also say something like this, where the current that goes in like that equals the current that goes like this. And if I run the math, what will pretty much happen is that I'll just get the negative values of this. So if the other direction indicates that it's a positive current, so in the old version where the arrow goes in the other direction, and if I1 is a positive quantity, in this setup, I1 is going to be a negative quantity. So that pretty much means that the current goes in the opposite direction, vice versa. So when it comes to these sorts of calculations, it doesn't really matter what you select ultimately as arrows and like which way is the right way or wrong way. Because if you select the wrong way, you'll figure it out very easily if you actually selected it the right way or not. Okay, so let's go ahead and apply Kirchhoff's current law to an actual circuit. I'm just going to just draw an example over here. It's going to have a voltage source. Typically, when you see voltage sources in circuits, it's going to be a circle with a plus and minus. Plus indicates the more positive side, and minus indicates the lower voltage. I'm going to arbitrarily select this to be a 10-volt difference. And then this go ahead and connects to 3 different resistors. So there's one resistor over here. There is another resistor over here. And there's going to be one more resistor, just for the sake of it. And I'm going to make this one 10 ohms. I'm going to make this one 5 ohms. And I'm going to make this one 2 ohms. All right, so the inherent idea, again, the Kirchhoff current law, let me just use a different color to indicate arrows. I'm going to use black. So the idea is that the current flow in this direction, I can arbitrarily select any direction of current flow. I'm just randomly picking one. I can assign the arrow to be in the other direction, it doesn't matter. But the inherent idea is that I'm going to call this current 1. It's going to equal to the sum of the currents that go in here, so one that goes down here, another one that goes down here, and another one goes down here. I'm going to call this one I2, I'm going to call this one I3, and I'm going to go ahead and call this one I4. So I therefore know that, using the Kirchhoff current law, I know that I1 is equal to I2, and I know that it's the sum of I3 and I4. All right, and we know that through Ohm's law, the voltage is equal to the current times the resistance, and we have these resistors with set resistances. And again, because the top right here, this is a node, so effectively, let me use a different color, so this is effectively one node. This node contains a set voltage. In this case, because it's voltage, it's 10 volts right here, this is 0 volts over here. So 10 volts is right here, and there's 0 volts over down here. So this entire top set has a voltage of 10, and the bottom over here, the bottom node set right here, has a voltage of 0. So with that, let me go ahead and just quickly calculate what I2, I3, and I4 are using this entire setup, and I can therefore calculate what I1 is. So let me just go back to black. I know that with the resistor setup, I know that the current across the resistor is equal to the voltage divided by the resistance. So I'm going to go ahead and just throw that out there. So I know that I1 is equal to I2, when I2 is 10 volts divided by 10 ohms, so 10 volts divided by 10 ohms, plus I3, and I know that I3 has 5 ohms and it's at 10 volts, so I know it's 10 volts divided by 5 ohms. And I know that for I4, it's 10 volts and 2 ohms, so it's 10 volts divided by 2 ohms. So I can go ahead and just run some quick math. I know that I1 is therefore equal to 1 amp plus 2 amps plus 5 amps, which therefore means that I1 has a total current of 8 amps. And that's just a basic example of how you can apply the Kirchhoff current law. In fact, you can go ahead and test this yourself. What you can do is actually change the arrows, flip them around, and you'll find out that you'll get every voltage, that you get all the currents as negative values. You can go ahead and try that yourself. And the trick to keep in mind is that when you go ahead from 0 volts to 10 volts, you're not going to, the voltage difference is not 10 volts, it's negative 10 volts. That's something to keep in mind when you do that calculation.